Okay, I want to go over how to solve this kind of problem. So this is a more complicated linear acceleration problem. This is a two-stage problem. So a rocket is launched vertically and accelerates at 12.5 meters per second squared for 2.50 seconds. So it's leaving the Earth's surface and it's accelerating upwards at that rate. At 2.50 seconds, the engine shuts off, and now it becomes a free fall object, meaning it's under the influence of gravity at this point. Questions that you would need to answer in this particular kind of problem: how high does it rise to the peak? How long does it take to reach the peak? Now, this is going to be the total height from the launch pad to the peak, and then the total time from when it left the launch pad to when it got to the peak. Okay, so just to visualize, what's going on here and break it into different parts. Okay, so here's the rocket. It's on the launch pad, ignition. It's leaving the launch pad, and it's accelerating at 12.5 meters per second squared, and it reaches some height. And at that point, the engine shuts off, and now the acceleration becomes negative 9.8 meters per second squared. But it has accumulated some velocity at that point. Okay, so it started on the launch pad at zero velocity, and at this point where the engine shut off, it has some final velocity. Right? Now that final velocity is in the positive direction, so it's kind of like the second stage is like me throwing a ball straight up in the air. Right? So it's going to rise while gravity's slowing it down. Eventually it gets to the peak, and at the peak it turns around and comes back down to the ground. So I want to know how high it gets all the way to the peak from the launch pad and what that amount of time was. So there's two parts, okay? The first part is from the launch pad to 2.5 seconds, and then the second part is from the 2.5 seconds to the peak. Okay, part one. V initial 0, V final, we don't know. We know the time, it's 2.50 seconds. We know the acceleration is 12.5, and we want to find height 1, okay? So if we look at our list of equations, we have an equation for the change in displacement, which ends up, you can rewrite it as the final position equals the initial position plus initial velocity times time plus 1/2 acceleration times time squared. If I put in h where I see d for displacement, it's just going to be written this way. Okay, the initial height is 0, the initial velocity is 0, so those terms cancel out. So the height after stage 1, okay, stage 1 being the thrusters, the rocket accelerating upwards, comes out to 1/2 the acceleration times the time the thrusters are on for squared. So I put those numbers in, and I get 39.1 meters. Okay, so that's how high it rises before the engine shuts off. Okay? All right, next. What's the velocity at that point? I'm going to need to know how fast it's moving at that point, because that speed is going to project it up to the peak. Okay, the faster it's going at that point, when the engine shuts off, the higher it's going to end up going. So V final equals V initial plus acceleration times time. Again, V initial is 0, so it's just the acceleration times how long it acted for. So 12.5 times 2.50 comes out to 31.3 meters per second. Okay, so now I know how fast it's going when the engine shut off. Now that V final from part 1 becomes the V initial for part 2. right? So just make sure you understand where that's coming from, why, I'm switching it. I'm dividing this into two parts. So now part 2, the V initial is whatever it ended up with as the V final from part 1. Okay, so let's solve part 2, what happens after the engine shuts off. So let's think about this. In part 2, the initial velocity is 31.3 meters per second. That's what I solved for as the final velocity from part 1, right? The final velocity at the peak is 0. The acceleration acting on the rocket is gravity, which is negative 9.8 meters per second squared. And then the initial height for the second part is whatever I got for H1 in part 1, which is 39.1 meters. H2 is what I'm looking for, which is how high it rises to the peak. And then T2 is also what I'm looking for, which is how long it takes to get to the peak. Right? Once I get that information, I can add it to the starting time or time from T1, part 1, and then I can add it to how high it rised in part 1. Okay, so let's go through these equations here. All right, so we know that the velocity at the peak is 0. We know the initial velocity is 31.3, and the acceleration is gravity. So we're going to just take this equation and solve for the displacement, which is going to be height 2. When I bring the initial velocity over to the left of the equal sign, it becomes negative, and the acceleration is gravity, which is also negative. So just showing you that the negative signs end up canceling out here. Okay, so when you look over here, you'll wonder why there are no negatives for 9.8 for gravity. That's why it got canceled out. So my displacement equation becomes the initial velocity squared divided by 2 times gravity. Put the numbers in, I get 50 meters. So that means that when the engine shut off, the rocket continues to rise an additional 50.0 meters. Okay, now how long does it take to do this? All right. T2 is going to be equal to the initial velocity divided by gravity. And this just comes from that equation, V final equals V initial plus acceleration times time. The V final is 0, so when I subtract the V initial from both sides, it's negative, and then that negative cancels the negative gravity. So this is what I get from my time equation. Okay, it's whatever that velocity was divided by the rate of acceleration. Okay, so that turns out to be 3.19 seconds. All right, now the final max height, right, height from the launch pad to the peak is the initial height from part 1, okay, or sorry, height 1 from part 1 plus height 2 from part 2. And then the total time is the T1 time plus the T2 time that I just solved for, right? So the answers you get 89.1 for the height to the peak from the launch pad and 5.69 seconds for the total time.